Langton, Kaufman, and others working in the area of emergent computation and artificial life have made many discoveries about self-organization, evolution, life, and intelligence. But they are also doing science in a new way. They study systems that are highly nonlinear. Traditional scientific analysis works only on continuous, linear, stable, and smoothly changing phenomena. Langton describes how these two classes of problems require different approaches. He starts by examining the traditional approach, called analysis, in which scientists attempt to understand a system by examining the individual parts that make it up.
Traditional scientific analysis is most fruitfully applied to linear systems. Such systems can be taken apart in meaningful ways, the resulting pieces solved, and then the solutions obtained from solving the pieces can be put back together in such a way that one has a solution for the whole system. Analysis has not proved anywhere near as effective when applied to nonlinear systems. The nonlinear system must be treated as a whole.
If we study a linear phenomenon, we break it apart into its constituent parts and study them independently. But in studying nonlinear systems, Langton says we must begin with separate but related phenomena and then synthesize their behavior.
Rather than starting with the behavior of interest and attempting to analyze it into its constituent parts, we start with constituent parts and put them together in the attempt to synthesize the behavior of interest.
Synthesis is the approach used by Lindenmayer when he grows elaborate fractal plants from simple components, using simple rules applied repeatedly. It's not the approach traditionally used by biologists. Langton elaborates.
Biology has traditionally started at the top, viewing a living organism as a complex biochemical machine, and then worked analytically downwards from there, through organs, tissues, cells, organelles, membranes, and finally molecules, in its pursuit of the mechanisms of life. Artificial life starts at the bottom, viewing an organism as a large population of relatively simple machines, and then works upwards synthetically from there, constructing large aggregates of simple, rule-governed objects which interact with one another non-linearly in the support of global dynamics.
Langton is describing a process of emergence.
The key concept in artificial life is emergent behavior. Natural life emerges out of the organized interactions of a great number of non-living molecules, with no global controller responsible for the behavior of every part. Rather, every part is a behavior itself, and life is the behavior that emerges from out of all of the local interactions among individual behaviors. It is this bottom-up, distributed, local determination of behavior that artificial life employs in its primary methodological approach to the generation of lifelike behaviors.
To try to understand living systems with a global or top-down analytical approach is simply not feasible. It can produce only mechanical ducks. Though such contrivances may appear convincing, they have virtually nothing to tell us about the nature of life or about any other complex self-organized entities. Langton explains why.
Most of the more serious attempts, particularly during the long history of clockwork automata, involved a central program of some kind, which was responsible for the model's dynamic behavior. Whether it was a rotating drum with pegs tripping levers in sequence, a set of motor-driven cams, or some other mechanism, the tune to which the automaton danced was called by central control machinery. And therein lay the source of the failure of these models, and in my view, the source of failure of the whole program of modeling complex systems that followed. The most promising approaches to modeling complex systems like life or intelligence are those which have dispensed with the notion of a centralized global controller and have focused instead on mechanisms for the distributed control of behavior.
This conclusion holds true even for the latest sophisticated robots. Distributed control also seems to be better for the so-called expert systems developed by scientists who work on artificial intelligence. Langton says there are lessons here for our understanding of the natural world.
The most surprising lesson we have learned from simulating complex physical systems on computers is that complex behavior need not have complex roots. Indeed, tremendously interesting and beguilingly complex behavior can emerge from collections of extremely simple components. This leads directly to the exciting possibility that much of the complex behavior exhibited by nature, especially the complex behavior that we call life, also has simple generators.